Since we discussed Newton's laws, a thing happens that I do Newton's laws, and it gives me a description of how the constraints and conditions of nature, that we call forces, can change the motion of an object in time. That's what Newton's second law is all about, F equals ma, where the acceleration is the second derivative in time of the position. And then we just did a whole bunch of work energy stuff, but really, I started work energy, if you think back to it, I started work energy applying Newton's second law, because I asked the question, how do forces change the motion of an object in space? And in doing that, I sort of created the notion of work, and the consequence of the work is a change in a new quantity called the kinetic energy. And I realize that there are many such quantities, and I discover a fundamental symmetry of the universe that is sort of embedded in that. So everything seems to center around Newton's second law, and it's true that all of our classical mechanics has Newton's second law as the anchor. And today, I'm going to begin again with Newton's second law. Newton tells us that if we can determine the net force, that is the vector sum of all forces that act on an object, that from that we can determine the acceleration in proportion to the mass. Very, very familiar to us right now. Very familiar to us and to all students of physics, but not really the way that Isaac Newton himself would have described it. Because Isaac Newton, if you go and flip through the Principia and read it, it's a very dense read but enjoyable. If you flip through the Principia, you'll find that what Isaac Newton refers to most commonly is what he called the quantity of motion. The quantity of motion, according to Isaac Newton, was the mass and the velocity conjointly, a fancy word in Newton's time for multiplied. Because Newton realized that in changing the motion of objects, it was not only their velocity that mattered, but their mass as well. A simple example is, if I see one of you running down the hallway, I could exert a force on you and stop you quite easily, because the force that I exert in proportion to your mass produces a large acceleration, according to Newton's second law. But if I step out onto the train tracks and try to stop a freight train that is traveling at the same velocity, it's a very different issue. And Newton realized this, so he would rather not write Newton's second law this way, but in a different way. And so I'll proceed this way from Newton's second law, writing this the mass times what I know the acceleration to be equal to, which is the derivative of the velocity with respect to time. Notice that I'm keeping my harpoons as I go. I'm quite keen on making sure that I maintain the vectorness of this as I go through. It's really important. Well, the mass is a constant with respect to time, but as I've toyed around with this before, I would not be surprised to bring the mass into the derivative. It was never actually in there in the first place, but I'll bring it into the derivative now. So I have the derivative of a specific quantity, the mass, multiplied by the velocity, that quantity of interest to Isaac Newton divided by dt. Well, that quantity, mv, the quantity of motion, has a modern name and a symbol that goes along with it. It's given the symbol lowercase p, so I'll write this as the derivative of p with respect to time. This is the way Isaac Newton would write the second law. This quantity p, a vector quantity, because its derivative is related to the net force, which is of course a vector, is of course what we know as the momentum. The momentum. A vector quantity whose units can be found by looking at this relationship that the net force is equal to the derivative of the momentum with respect to time. Multiply time to the other side, force in newtons, time in seconds, and the unit of momentum is the Newton second. There is no more, well, I suppose there are other systems of units for that might be useful in other brands of physics. But in classical mechanics, there is no momenton or any more fundamental unit. So you'll see me writing and saying Newton seconds of momentum. The momentum is a quantity that has special properties, just like work and energy. It's not a better version of Newton's second law per se, but I'll find as I work with the momentum that it reveals an interesting fact about the nature of things that I might not have otherwise realized. So let me get into manipulating this new version of Newton's second law and see what I can discover. First, I'll point out that writing this as the net force, sigma F, darn it, like this, that sigma F, the sum of all the forces, is equal to the derivative, I'm just rewriting here, the derivative of the momentum with respect to time. I can rearrange this equation to solve for dp. So dp, the differential of momentum, would be equal to the net force, also a vector, dt. Well, I can't let that stand. Obviously, it's screaming for me to integrate both sides of that equation. And when I do, what I'm going to get, naturally, is the integral of dp. It's the sum of all the infinitesimal changes in the momentum, which naturally is the total change in momentum, delta p. The change in the momentum is equal to the integral of the net force dt. A calculus version of a law that many of us have already encountered in our previous studies of physics. This quantity, delta P, gets its own special name. It's called impulse. Impulse. Doesn't look much like an M there. But impulse, the change in momentum, naturally the units of impulse are Newton seconds. If it's the change in momentum, the final momentum minus the initial momentum, then the impulse would have units, the same units as momentum, Newton seconds. Because the change in momentum is equal to the integral of the force dt, I encounter a useful, utilitarian notion when I make a graph of the force as a function of time. Imagine that I have a force acting over time. It changes in some arbitrary way like this. It's quite general. When I perform the integral of f dt, I'm finding the area under the curve. So a nice little generalization that can be useful in problem solving and scientific investigation in general is that if I find the area under this, the area is equal to delta P. The area under the force time curve is in fact equal to the impulse. I have to have a little caution when I'm working with impulse, take a little bit of care in the context of problem solving, because momentum is a vector. When I calculate the change in potential energy is a scalar quantity. Sure, it can be negative, but I endeavor always in my problem solving to make the lowest potential energy zero whenever I can, so the potential energies are always positive. I'm simply subtracting. But
Initial.
I'm not sure how you mean that.
Like delta P is not final minus initial.
Yes.
Consideration more than just like doesn't it take into consideration everything?
Between the final time and the initial time, I get the total change in momentum, because the change in momentum is equal to this integral. So the limits on this integral are from the initial time to the final time.
Okay.
Is the P we're using now the same one as the one over there? The top right? Is that not a P?
Oh, that's not P, that's a rho. That's a rho.
Oh, wow, I can't wait till we get to that.
So we have the power P.
Well, rho is not P. Rho is a Greek letter. It's not. Oh, well, you're going to be in trouble then. Point is, caution when manually calculating the change in momentum, because momentum is a vector quantity. And I could have a situation, let's get nostalgic for those who have already taken an introductory course in physics, that a pitcher throws a baseball toward the batter, and way to roll your eyes there, Karen. Pitcher throws a baseball at the batter, and the batter hits the baseball back. That change in momentum, when calculated, because the baseball has a mass and a velocity, has an incoming velocity and an outgoing velocity, that change in momentum, the final momentum minus the initial momentum, ends up being addition, because one of those momenta, however you choose your coordinate system, is negative. So you have to be careful when you're calculating the change, because it's a vector quantity, not a scalar quantity. It's not simple algebraic subtraction, it's vector algebra subtraction. So you have to be a little bit cautious in calculating the impulse, the change in the momentum. So this is all very practical and feels a lot like Newton's second law, and I can go back to all the Newton's second law problems I've already solved and cast them in this way and find that it requires very little change in order to think about it that way. But there's a consequence to this idea, and the consequence deals with a whole realm of physics problems that I can solve that we haven't encountered yet. Everything that we've done so far involves individual objects. Every once in a while in studying Newton's laws, we'll put one object in contact with another and they'll push and a push. But we have those objects, they're combined, they move at the same acceleration, or their accelerations are related in some simple way. What we have not addressed is a whole third of our Newtonian mechanics, and that is Newton's third law, the law of action-reaction, when two objects interact the one with the other, exerting equal and opposite forces upon each other. Such a case is called a collision. For example, if I have two billiard balls and they come in close proximity to each other and collide, exerting forces one upon the other which are equal and opposite. But the accelerations that occur are in proportion to the mass. And think about calculating those accelerations when the time of the collision is extraordinarily short. And try to get in there in the space in between during a collision and figure out what the forces are. It can be extraordinarily complicated, perhaps nearly impossible. But it turns out that there's a little secret thing embedded here in the notion of momentum that I'm about to reveal. Consider two objects, A and B, that collide one with the other. So I have an object A here, which is moving this way with a velocity I suppose I call VA. And I have another object B, and they're moving in a straight line, and I'm not going to let them deviate from this sort of straight line motion, so they're definitely going to collide the one with the other. A and B, they do not necessarily have equal masses. They do not necessarily have equal velocities. The only thing that's certain about this situation is that they will collide and come in contact with one with the other. So I will show you now, or draw the same situation again, but in a few moments in time later, when A and B are now in contact, the one with the other. While they're in contact, they exert forces of contact, electrodynamic forces between whatever. I want to stress something here. It is immaterial to me how complicated these forces are, as you'll see in a moment. I am talking about the collision between two billiard balls because it's very simple in the mind to imagine that they exert forces one on the other that are easy to draw. This argument works equally well, and I'll probably reiterate this. This argument works equally well in a collision between automobiles, for example, where there are a fantastic number of forces acting, the one on the other. But I'll come back to that in just a moment. For now, A and B, let's imagine that A exerts a force on B that I'm going to draw this way, because obviously A being to the left of B, it's going to exert a force, which I'll call FB, the force exerted on B. The notation of this is not critical. I just have to choose a scheme of notation and stick with it. So there's a force that acts on B by A, but according to Newton's third law, there must also be a force that B exerts on A that is equal in magnitude but opposite in direction. And so I draw a force that acts on A. So I can write this as a vector expression because I'm in one dimension. I'll choose, naturally as I do, the right to be the positive direction, the left to be in the negative direction. And so FB is a positive force and FA is a negative force, such that I can write that negative FA is equal to FB. Those forces are equal to each other and opposite in direction. Equal to each other and opposite in direction. Well, now I'm going to do things in a slightly different way, and I'm going to apply my new version of Newton's second law. My version of Newton's second law that says that the sum of the forces is equal to the derivative of the momentum with respect to time. But what I'm going to do is I'm going to do it on average. I don't have to, but it's just something that I'm accustomed to. It will make little difference, but I don't want to. I'm going to have a silly little integral to do at the end if I don't do this in advance. If the net force is equal to the rate of change of the momentum, then I can write this expression on average, as I can with all of these rates that we define in physics. I can write dp dt as delta p over delta t, and I'll do so here. The force then exerted on A, according to my new sort of impulse version of Newton's second law, is the change in momentum of A divided by the time in which A's momentum changes. It's the change in momentum of A divided by the time in which A's momentum changes. Must be equal to, naturally, the change in momentum of B divided by the time in which B's momentum changes. Well, you see immediately, these two changes in motion happen in identically the same amount of time, because the amount of contact time, or the amount of time in which the forces are being exerted, is identical from the point of view of either mass. So the delta t on either side here will cancel out. Those delta t's are gone. So what I find is a rather curious relationship which says the negative of the change of the momentum of A is equal to the change in the momentum of B. And so I'll spend a moment pondering that. What could that possibly mean? What it means is that when two objects collide, the one with the other, if the momentum of A increases, the momentum of B must decrease. And if the momentum of A decreases, the momentum of B must increase. The changes in momenta are equal and opposite. This is not true of accelerations, is it? The accelerations are not equal and opposite, because the accelerations, I have to consider them in proportion to the mass in order to understand this. But because I'm considering the quantity of motion, the mass times the velocity, the momentum, the changes in momentum are equal and opposite. So it's like you and I collide. When we collide, maybe during that collision, I give you some momentum. Therefore, your momentum increases by the exact amount that my momentum decreases, or vice versa. Because Newton's third law applies to all forces that act between objects. I'll reiterate again. Imagine a car crash where two vehicles come together, they collide head-on. There's bending of metal, and there's headlights and different shapes of things, and so there's normal forces all over the place. Every single one of those forces is action-reaction. Every single one. It doesn't matter how complicated. The force is now gone from the relationship, which means the inner nature of the collision force is irrelevant to this, which is a rather spectacular thing, and very, very lucky. If I had to in collisions between objects know the exact details of all the forces that take place during the collision, then this type of physics would be utterly impossible. But it turns out it's simple and transparent. A consequence of this idea that I've written here, what I'm going to do is take this thing and make it practical. And I'm going to flesh it out a bit, turn it into a practical rule that in principle I can use to solve problems. In fact, after we're done this discussion today, you can just go forward and solve all of the momentum problems that you would ever be asked in this level of physics. But here I go. Since the changes in momentum must be equal to one to the other, I'm going to flesh it out a little bit and write that the negative, this change in momentum of A, which must be the final momentum of A minus the initial momentum of A. Now, here's where things get a little squirrely. We're very accustomed in our physics to writing an initial quantity as, like the initial velocity as v naught, with a subscript naught on it. Or perhaps the subscript 1 or the subscript I in order to designate that. We do not do this for momentum. For momentum, the initial quantity of A's momentum is just the momentum of A. The momentum of B, the final momentum of A gets a prime. The final momentum of A gets a prime on it. When we consider, a little bit later on, a couple of days from now, when we consider that momentum is a two-dimensional quantity, we'll realize that making the final momentum prime is a really good idea. Otherwise, we'd end up with triple subscripts. So in order to avoid that, we have to change our notation a little bit so that the final momentum is a primed quantity. Yeah. Oh, there's still vectors. Yeah, you're right. I've dropped my vectorness as I go along. Well, actually, no. Now I am, in fact, talking about the magnitudes because there's my vectorness there when I wrote that negative sign there. That's where the vector was. But ultimately, the law that I end up with is a vector law. You're sort of right. So I'm sort of walking on the fence here of what is a vector and what is not. Yeah. Momentum is lowercase p. It is not capital P.
Just low.
Yeah, I struggle with it. I'm trying to dip them below the deltas. I don't know what it is a lowercase p in all cases. Capital P is pressure. Yeah.
Something like that. Would prime be a superscript for P?
Yes. Yeah.
If both be
Mm-hmm. Mm-hmm. And I have no idea how that works out, but I'm sure that it does. So I have the change in momentum of A on this side, and so using this new notation on the right-hand side, this is the right side, I'll write delta, or the change in momentum of B, which is the final momentum of B minus the initial momentum of B. This expression is A on the left-hand side and B on the right-hand side. What I'd prefer is initial on the left-hand side and final on the right-hand side. And so I just have a little rearranging to do. This negative sign is going to swap the order of this so that the initial momentum of A minus the final momentum of A is equal to the final momentum of B minus the initial momentum of B. And so I want to get all the final quantities over there. So I'm going to add the final momentum of A over there, and I'm going to add the initial momentum of B over here, so that I have the momentum of A plus the momentum of B initial. And these are vector quantities. Just for you, Jules, I'm going to throw the harpoons back in. Those are vector quantities. That's vector addition. I'm doing a one-dimensional problem here, but it would be vector addition in 3 dimensions. No problem. Is equal to the final momentum of A plus the final momentum of B. And so what I've discovered, quite remarkably, is that there's a quantity that I can compute by adding up the initial momenta of both objects in a collision. And that quantity must be equal to the same quantity calculated after the collision. That is, there is a quantity which I call the initial momentum, which is the sum total of all of the momenta in the system at some initial point, must be equal to the final momentum at some later time. It is, quite beautifully and spectacularly, another symmetry of the universe revealed by the judicious application of Newton's second law. It is the law of conservation of momentum.